In this video, we are going to find real numbers a, b, c, and d such that a cubed plus b equals c, b cubed plus c equals d, c cubed plus d equals a, and d cubed plus a equals b. Before we move on, don't forget to give a like, subscribe to my channel, and turn on post notifications. The first thing that I'm going to do is to add all four equations. So adding them, on the left we have the sum of cubes and the sum. On the right we only have the sum a plus b plus c plus d. So that means the sum of cubes must be 0. So unless all numbers are 0, we must have some positive and some negative numbers among the unknowns. Let's try to get more information about the signs of these unknowns. Start with a being positive. Under this assumption, if b is also positive, then from the first equation we can say that c is positive because the two terms at the other side are both positive. From this we can move on to equation 2. D is also positive, but this cannot happen because we've deduced just now that we can't have all four unknowns being positive together. So contradiction, that means b is negative. Then from the fourth equation, we can rewrite d cubed equals b minus a. So b is negative minus a positive number a, which is negative 2. So d is negative. And then finally, from the third equation, c cubed equals a minus d. And a is positive, subtracting a negative number. So that means c is positive. So under this assumption that a is positive, the signs of the unknowns follow the order plus, minus, plus, minus. Well, of course, if we assume the otherwise, which means if we assume that a is negative, then the signs will have the order minus, plus, minus, plus. So altogether, we know that a and c must have the same signs, while b and d must have the same signs, and those signs have to be opposite. The next thing that I'm going to do is to subtract the first equation by the third equation. So subtracting, we have a cubed minus c cubed plus b minus d equals c minus a. And now I'm going to rearrange that and get a cubed minus c cubed plus a minus c equals d minus b. The reason that I do this is that these two expressions has a common factor, which is a minus c. Taking that out, we have a squared plus ac plus c squared plus 1 inside the bracket. And I'm going to do similar things on equations 2 and 4. So we have b cubed minus d cubed plus b minus d equals a minus c. And we have the similar common factor. And now we're going to take a look at these two equations. Inside these two equations, we have both a minus c and something similar to b minus d. If I assume that both a and c and b and d are not equal, then I can say that a squared plus ac plus c squared plus 1 equals d minus b over a minus c, and b squared plus bd plus d squared plus 1 equals a minus c over b minus d. Now on one hand, the expressions at the right has a product exactly equal to 1. Sorry, minus 1. Because the d minus b and the b minus d have the signs swapped. But on the other hand, looking at the expressions at the left, they're actually both strictly positive. Indeed, a squared plus ac plus c squared plus 1 can be written as a plus c over 2 all squared plus 3/4 of c squared plus 1, and we can do similar things on the other expression about b and d. So now we actually have a contradiction, which is that we can't have a and c not equal and b and d not equal to occur at the same time. This means that we must say that either a equal to c or b equal to d. But if this really happens, say if we have a equals c, then we can go back up to the equations in blue. Say if a equal to c, then we can actually just say a minus c equals 0. But from this, we know that this implies d minus b equals 0 as well, which means d equals to b. Or if we have b equals d instead, then we use the other blue equation, and we have the same conclusion, which is that not just either one of these two has to occur, but both a equals c and b equals d has to hold at the same time. So now our system of equations becomes much simpler, because our system now then becomes, if we go back up, we can say that this is just a, while this is just b, and the other two equations can be ignored. So it just remains to solve a cubed plus b equals a, and b cubed plus a equals b. But if we add the two equations, we can quickly see that, again, the sum of cubes has to be 0, but this time we only have two unknowns. So that means a cubed equals minus b cubed, and we have a equals minus b. So putting this back into, say, the first equation, then we can say that, therefore, a cubed minus a equals a. So a times a squared minus 2 equals 0. Here we can also obtain the all zeros solution from a equals 0. Otherwise, we will have a equals positive square root of 2 or negative square root of 2. If we have positive square root 2, then that means b and d has to be both negative square root of 2, and c will also be equal to a. Whereas for the case a equals negative square root of 2, then b had to be equal to positive square root of 2 instead. Same for d. And c will be equal to negative square root of 2. And each of these quadruples is a valid solution. So this is our final answer. Please feel free to share your ideas in the comments. Thank you for watching. See you next time.